to study the effects from bronzed acidity, there is a challenge, which is that the coupled chapelite catalysts are dual functional. They provide both redox and acid functions. As properly trained researchers, if we want to study effect A from effect B, we want to keep only one parameter change, the other fixed. However, in this case, it is difficult to maintain redox site density and property and only change acid site density. And the same situation is true in other cases. So what we did is to compare catalyst with sufficient difference in the density of bronzed acid sites, and we only use kinetic data benign within the differential regime to do our comparison. This slide shows the ammonia TPD, and I will not go to the detail, just to show that we use this technique to quantify the number of bronzed acid sites in each unit cell of our catalyst. Then we did NO oxidation, ammonia oxidation, and SCR reactions. This slide shows NO oxidation results. Both us and the researchers from Purdue concluded that this reaction it cannot be catalyzed by copper ion monomers. So therefore, we prepared samples with relatively high copper loadings to generate dimeric species. And the interesting finding is that our catalyst with the highest silicon to aluminum ratio at 35 shows apparently higher thermal frequencies compared with the sample at low SiO ratios. So there might be two explanations to this. First, the dimeric copper species, the active sites, might be more readily formed at a high SiO ratios. And second, the redox barriers might be more readily overcome for the samples at high SiO ratios because the interaction between the framework and the catalytic centers are weaker. And also we want to point out that bronzed acid site density plays no beneficial role here. The sample with the lowest density of bronzed acidity shows the highest activity. And the situation is much more complicated for ammonia oxidation. For ammonia oxidation, we do both low and high temperature reactions on samples with copper loadings that we believe are fair to compare with. In the low temperature regime, the situation is really complicated. We know that from this our news plots, the activation energy on different catalysts are so different, and the reaction rates cross into each other. Therefore, we are still not sure what we are really understanding this, but probably we can conclude this, that the redox and acid functions both play significant roles to cause this complexity. The high temperature regime, the situation is much more simpler. These two samples with SiO ratio 6 and 12 are very similar, but apparently the activity is lower than the sample at SiO ratio 35. This probably means that the catalytic properties in ammonia oxidation between copper 2+ and copper OH is different. Copper OH seems to be much more active compared with copper 2+ for ammonia oxidation. And there might be a transition in positioning of those species as a function of temperature, because we see this transition in our news plots at temperature around 470 Celsius. And finally, the standard SDR reactions, we also did low and high temperature measurements. In both cases, there is a clear beneficial rule identified on bronzed acid sites. And in both cases, samples with low SiO ratios, high bronzed acid density, shows apparently higher thermal frequencies in both regimes. On this slide, we plotted the density of bronzed acid sites monitored with ammonia TPD and the SCR reaction rates. This shows the low temperature regime. That we have a not bad linear relationship showing that the density of bronze SSS really benefits SCR reactions at low and even high temperatures. And we tentatively give this a rate equation that includes state ammonia term. This does not necessarily to be NH4 plus. It could be weakly bound ammonia that complexes with ammonia that are reactive, as suggested not a long time ago by Nino. With that, I go to the conclusion page. I think I covered the following things. We synthesized and utilized multiple copper SS13 catalysts with various SiAl and CuAl ratios in order to reach a more general understanding of the SCR chemistry. We discussed copper ion location, mobility, and possible interconversions in various environments. And we identified different temperature-dependent kinetic regimes during ammonia SCR. At least this can be qualitatively described from mobility and interconversions of copper ion active centers. And finally, it is difficult to disentangle redox and acidic contributions in SCR, especially since there are strong dependence on reaction temperature, SiAl ratio, and copper loading. But still we can come up with those conclusions. The NO oxidation follows the redox mechanism and catalyzed on oligomeric copper ion species. Acidity does not play a direct role for this reaction. Ammonia oxidation heavily depends on temperature, SiAl ratio, and copper loading. Both redox and acidity likely play important roles. And finally, bronze acidity appears to promote standard ammonia SCR. It might be an indirect way. Acidity favors the reaction result being an essential ingredient of the active site and hence the reaction mechanism. And with that, I will acknowledge our DNOX research team at PNNL and DOE the facility AMSO. We carried out our research there, and financial support from DOE Vehicle Technologies Office. I'd also like to acknowledge our industrial partners from Cummins and Johnson Massey, and also collaborators from WSU, Purdue, and Notre Dame. With that, I thank you very much for your attention.
Questions for Feng? We're going to make these sprints, okay. Please state your name and affiliation.
Stacy Zong, Chevron. There's, I think, one small, let's say, bookkeeping measurement or number, and it may have no impact on your measurements, but I'd be curious about it. When you synthesize the material of the silica to aluminum of 35, what else is counterbalancing the cation in the synthesis? In other words, typically you have a lattice defect in the wall. And so how does that influence any of the numbers that you've measured? In other words, the treatment you've done is as though the defect has no impact. So I'm asking, is it possible it has some impact, and then how do you account for that?
I'm not sure I catch your question very well. And,
so Stacy's question was, when you make, he wants to know how you made SOZ13.
Right.
35. And if you use adamantimonium, for example, there's not enough charge on the lattice to balance all the charge on the SDA. And the way you do that is to make a defect site in the lattice in place of an aluminum. So he's predicting that at such high aluminum, or a silicon aluminum ratio, depending on how you make it. There could be defect sites in the lattice.
Oh, yes. I think I do have some animal evidence to show that we have pure silicon impurity in that material that we synthesize. But the signal is not very strong, judged from our silicon animal measurement.
Okay, in the interest of time, please join me in thanking Feng one last time.
Session. It's going to be presented by Alex Bell.